Which one?
The longest one, like
The
the.
longest one, the laboratory.
Yeah.
You said you're gonna do that?
Yeah. Oh my god, I didn't even staple the papers.
Isabella! Nice to see you!
I didn't even staple the papers together. What?
Okay.
Okay. You're ready.
So let's do this paper. So based on
Thomas, did you start?
Yeah, sorry.
yeah, so that's a paper I thought my advisor should, but it turns out it's not her. So but it's still creating stuff about something I like, and so that support me to read it through, and based on most people trying to read it, so it's not that hard paper. It's actually straightforward enough to understand. So I think I will go through it with you guys. So here's something we need to know about biology before reading this paper. The first thing is for every biomaterial paper, their ultimate goal is just to save people or save world. And every paper just about biomaterial will try to explain it, but in a specific way. For example, if they want to save people, they will just talk about their material will cure cancer. Their material will cure a kind of human disease. But in the beginning, they will say this material will cure cancer, but usually in the end of the paper, you will find out and their material will just cure one specific cancer and even just only some cells in that cancer. So that, for me, that means bad. And
I disagree with the first statement.
what?
Because in the second word, they were trying to create biomaterials to kill people. Actually.
What?
So, yeah.
That makes
Oh, yeah,
sense.
sure.
Yeah. So and for this paper, they will.
That's not ethical science.
But they did. I mean, they did.
Yeah.
Were there a lot of research papers about it though?
Yes, they did. Many research, you know.
No,
like-
do you have a paper on it?
Yeah, it's like
I watched a documentary. I don't know if there is paper for sure. There is.
It shouldn't be out there.
Yeah, and for this paper, it's obviously the latter. So it wanted to save the world. So it wanted to protect the environment. That's always a thing. They want to protect the environment. So they want to reduce carbon emissions. So in this paper, they are calling it carbon sink. You know, one specific one important thing of this paper is I don't know why the author he's captain use a fancy word. So he can just say he reduced the carbon emission, but instead he said something about carbon sink, and it's just the same thing.
Okay.
And then there is some basic about cells, but I don't think that's important. Just I try to write them. So we have there are two kinds of cells in biology, and for this paper, because they are using some very simple cells, so so they are using who can tell me how to read that word? I don't know.
Which one?
prokaryotic.
Prokaryotic. Okay, they are using the prokaryotic cells. This is the kind of cells without nucleus, and I don't think that's important. Just some basic knowledge, because for us, we ourselves have nucleus. Clearly, we have DNA in it, and the third point is something a little. I think it's a little important. It's some basics about protein. So we all know the protein has some structure. So they have primary structure, secondary structure, tertiary structure, and the higher structure. But all we need to know is the primary structure and secondary structure. So for primary structure, it's a basic thing about the amino acid. So in the amino acid, okay, I need to go. So in the amino acid, we can say they all have the COOH and they all have the NH2 on two sides. So when two amino acids are bonding together, they lose one water, and then they form the peptide bond. It's an NHCO. That's a basic. That's some very basic simple protein. And if the chain keeps going very longer, then we can get a protein chain. And through this protein chain, there are 3 different kinds of secondary structure, and it's also talked about in the paper. So there is alpha helix, beta sheet, and random coil. So since if you read the paper, you know something basic that beta sheet has higher strength and stiffness than alpha helix, and that's a example of the protein. So we can that's not important, just some knowledge. So the red curve, the red helix is alpha helix. That's why it's called helix. And for the beta sheet in that paper, it's those yellow arrows, and the green random strings are random coil. So there are just 3. And all the proteins we saw are the combination of these 3. But it doesn't mean every protein has to have these 3 parts. Some of them just has maybe alpha helix and beta sheet or something, but it at least has 1. So I think that's enough for our background. And okay, we come to the paper. So
Did you say the alpha has a stronger strength than the beta?
No, beta is stronger than alpha.
Okay.
Alpha, yeah. So
Do you know why?
yeah, I know actually. So I don't think I know all of it, but based on what I learned, so because you use alpha helix is that a helix structure, so if it will be very easy to become.
Yeah, to bend it and
Yeah,
deform
and
it
then
basically.
if it fall apart, then it will. But for beta sheet, it's just an arrow
Sheet,
thing, like
yeah.
so. It will be more strong.
Yeah, sure.
So for the goal of this paper,
You have
Is
another
it
ground?
strong?
what?
I didn't really get it. Why is it stronger?
Because
The structure.
alpha helix, they are a helix structure, and
Oh,
if you higher up or something, their helix will be easy to go to the direction.
I see.
Yeah, but for beta helix, just arrows.
If I'm not wrong, so the alpha helix is mainly hydrogen bonds and mainly, you know,
The other one's like covalent bonds.
the other one, I think so, right? Sulfur connections, sulfur
Disulfide bond.
sulfur bond, the
Yeah.
beta helix. That's
But
why.
I think the main thing it says in the paper, transition from alpha helix, which is intramolecular connections, to beta sheets intramolecular.
Yeah, exactly. So
So
the
instead of being self-coiled, it's coiled with different parts of the sheet.
Yeah. Oh yeah. Okay.
so one of them is just hydrogen bonds. The other one has, you know, intramolecular. The other one is just intra.
But those intermolecular could still be hydrogen bonds.
Oh yeah, you're right.
Yeah, it might
Yeah.
not necessarily be a disulfide bond, but for the alpha helix, you just have the hydrogen bonds between one part of the helix and the next part of the helix. So that's just within one coil, whereas this is between 2 different sheets that are 2 different sections. They might not be anywhere near each other if you like took this, like the peptide, the sheets could be over here and over here, and they would hydrogen bond over here, and a bunch of random crap could be going on over here. It doesn't matter.
Yeah.
So for the goals of this paper, so clearly, because I said they wanna aim at protecting the environment, so they want to produce a self-bonded recycle and backyard compostable. That just means it can degrade. I don't know why they still say that in some fancy words, but it's okay. It means it just means it's
Biodegradable.
yeah, and with very attractive mechanical properties. So for the mechanical properties, most of the time they just measure the thing I listed there, their strengths, their modulus, and compare these properties with other materials that is already in use and try to verify their material is the best. And and also their material is very clean because according to them during the production process they don't add any binders or additive.
So now that I thought was interesting because then they had a whole section about the binders and additives that they added that make it stronger.
Yeah,
Like-
so they're like, oh, our thing is really good. We don't need this thing, but we're still gonna try some to make them stronger. So I was like, okay.
And then also in the conclusion, they cite the values they got from the binders, not from, because that's the more impressive values, because the binders make like 300% increase in
Yeah,
mechanical
but-
strength. But that's with the binder.
Yeah, so
That's the nasty stuff.
No, it's fine. Who cares?
The binders weren't particularly
I don't think it's an
either.
issue. They actually use CNFs in this paper.
Weren't there like cellulose kind of
Yes,
binders?
yeah. I don't know if they use crystals or fibers, but
I think it was fibers from what I remember.
yeah, there's some fiber.
that's what I do research
Fiber.
in. Oh, they use bacterial cellulose, so the bacteria makes the cellulose.
Yeah,
So
yeah,
a little
yeah, that fiber is based on. Okay, and why they use the algal? Because it's a lot and it can grow faster. That's what I think is interesting. They said if you want to use algal, you can just plant them somewhere near where they're gonna do the experiment, and you just take the algal. I was like, okay, so because algal is also portable and very clean carbon sink. Yeah,
Right.
you can just dump them anywhere, and then they can just become dirty. So that's based on their very grand goal, and then what they did is they got the cells they need from the alga, and then they use them as powders and try to fit them in the mold and through the hot pressing. But I don't think this part how they made them is very important. It's just I think we just need to know. We just need them through hot press, and then what they get is a kind of that long stick thing. And then and the figure F is they just throw them in the dirt and try to figure out how long it's gonna become weaker and weaker and how long it's gonna be gone. So try to prove their material is clean. So so the and then they of course after they get their material, they try to characterize them, try to know the basic mechanical properties of their material. So that's what they did. They try to add some pressing force based on different temperature. They try to know the relationship between the stress and the strain, try to get the modulus, and they try to get the stress. So from this figure we can see when the temperature is from 120 to 160, they have the most amazing pressing force. It's like the number is the biggest through these all, and the pressing force they add is 7 here, 7 kilo. And
What are those like numbers in the middle?
you mean these numbers?
Yeah.
They're the strengths. they
Okay.
get.
The
strength,
plus
the
your
strength.
strength on the
Okay.
Yeah,
right hand side.
Okay.
They're the strengths they get. So
Yeah.
they try to. So their conclusion is if the temperature is higher than 120 and not higher than 160, then they will have the if the pressing force is 7, then they will get the best strength. And then because they already know the temperature they want to use is not higher than 160, so they still try to measure the strength, and then we can see the strength is best when the temperature is 140, then they will have the highest strength. So they got the strong dependency of the strength of their materials with the temperature. So and because of the relationship between the strength and the time, the strength first increase and then they are still, so they try the time they use it they try to pick up a middle time to make their experiment result very convince people. So and because they already showed their material is good. It has very excellent mechanical properties. So they want to find out what bond made it so good. So they do FTIR and XPS. So from the FTIR, we can see there are 3 different color of lines: the green one, blue one, and I think it's orange one. So from the numbers we can see the green one and the blue one. These numbers are not that much different, but the difference between the blue ones and the yellow ones, their difference is greater because for this part, they are just 3 amide, 1, 2, and 3. So we can see the green one, the blue one, they are basically the same, and and there is much difference between those 2 one. And this one and this part is the oxygen hydrogen bond. So from this we can use during the pressing, more beta sheet is formed, and because I already said beta sheet has more stiffness, so that explains why during high temperature their mechanical properties are so much better. So these blue ones, they call the poorly bonded their material because they are just in 60 degrees, and these ones are 140 degrees, and from above we know when temperature is 140 degrees, the strength is the best. So, and then from the XPS we also know there is a decrease in these 3 bonds, but there is increase in carbon-carbon and carbon-hydrogen bond. That is because for their matrix, their cell matrix, they are made of protein and carbohydrate, and most of the matrix is protein, and some of them are carbohydrate. But that's why the shift to more beta sheet is important, and because the bonds that are decreased is mostly in the protein and carbohydrate, so that matches their assumption. And they suddenly realized, so they should not just use a cell. They should first sonicate the cell and then use that cell. So I don't know why they do it at the beginning. So suddenly do it. Oh, okay, we will sonicate the cell, but it's okay. So they prove if you sonicate the cell and mix up that, and then it will become better. So the thing is, why do you want to make the cell dead? It's okay. Yeah.
I thought
I
it wasn't
think-
to make them dead, but more to like break them apart and have more surface
But
area.
if you sonicate them, the cell must be dead.
Right. I think they just wanted to expose the proteins more, I think.
Oh,
But I have
Yeah.
a question on the
Surface
last.
treatment.
Could we go back
Yeah.
to the IR?
yeah.
So it says that there's an increase in carbon-carbon bonds. Where, like, I'm a little confused on how they're quantifying this information to confirm that.
The XPS or the FTR?
The
XPS.
FTIR.
What?
The FTR.
Yeah.
Yeah.
I think through FTR you cannot get which bond is increased. They are getting the
Okay.
from
So they're just
XPS.
saying from XPS, they're saying the FTIR just shows the presence, they're not saying that quantifies anything.
Yeah.
Yeah,
Okay,
that's how
cool.
they're-
Yeah, and I was actually thinking because in the FTR exam, they usually when you interpret FTR, you kind of have the sheet where you know which bond is which wave number and stuff. So I'm just assuming if there's a question in the exam, how they are gonna frame an FTR question.
Yeah.
Because if did they say in the paper maybe the peaks at maybe 3,274
Right,
is
those
OH
age
bond.
Yeah.
Yeah. How would
That's
you-
all I know.
Yeah, but if they say that, if they say that in the paper, and they can just ask you, and since you have the paper there, you can check. But
I think
Right.
it's in the
Yeah.
paper.
yeah, Yeah. If
So-
not, yeah.
And they can't quantifiably say anything about the H bonding through XPS because they don't have that because they have
Yeah,
C,
they have C.
CC, CO,
Yeah.
C double bond O. They don't have any OH.
Mm-hmm.
So I'm wondering why can you not do that on XPS? I don't know XPS that well. Too strong, too weak.
What? Say it again.
So it doesn't. They don't have any peaks for the OH bonds, which is something they wanted to quantify, which is something like a claim they made for the IR, or maybe they're saying there's a shift in the peak rather than an increase in intensity of the
Yeah.
peak in the IR.
It might just
Yeah.
be too.
No, crazy. Yeah,
Yeah.
that would make sense.
So much.
I mean, they have a CH,
It's true.
but it's also a CC.
I think in this paper they just said H bond is not necessarily related to the formation of beta sheet.
Right, which also confused me because isn't it?
I
I don't know. I'm not that.
I mean
I took biochem once.
Which is the one that you cannot use to characterize bigger atoms. That is related with XPS too.
The one you can't use to do what?
There is someone that you can use to characterize the quantity of your atoms, right? The amount in terms of concentration.
Oh, okay.
Using some technique that's similar to XPS, I don't remember. And that's not useful for
Okay.
more than carbon. I think
Raman?
No, it's not Raman. it's the quantities.
Okay. But Raman is
it's-
usually carbon.
For carbon?
No.
Is it NMR or something?
You cannot
NMR.
No,
quantify
that just tells you where things are in a molecule.
because it's similar. That's why I was thinking maybe it's something related to that. That's why they is maybe due to the
Maybe.
technique, not due to the. I think it's due to the technique and not more.
Okay.
No about the
There's a handheld.
the problem itself or whatever.
Oh yeah. Yeah.
What?
Yeah. A handheld XPS. Oh no, it's XRF. That's it.
Okay.
Yeah.
X-ray
Yeah.
fluorescence.
Fluorescence.
Yeah.
Very different. Very different.
Yeah. It's used mostly for like ceramic compounds and stuff.
That does sound like a no. Fluorescence, not the.
Can
I have a-
someone go ahead?
I have a question. What is amide 1, 2, and 3 bands?
what?
It says like the thermochemical processing at these conditions cause this is like the shift in amide 1, 2, and 3 protein bands. Like I don't know what those are or why the significance of like seeing those shifts
Where is
specifically.
In the
Page 4 of 13, like in the middle of the last paragraph.
I highlighted it.
I just didn't know like what those like I understand the concept of those bands shifting and then specifically in the poorly bonded to well bonded means that you have an increase in the beta sheets which increases stiffness and then you get better mechanical properties. But what is an amide 1, 2, 3 band for proteins and like why are they specifically like why is it those bands are the ones
Yeah.
that we quantify beta sheet formation?
I think it would be typical to like FTR of these kind of biomaterials, but I don't know.
Yeah, just like I'm not a bio. I mean, the last time I took a bio class was high school, and I don't know what an amide band is.
I think so.
Amide, amide.
So.
Yeah.
No, these are bands. This is not related to what do you mean?
It's really the FTR.
This is literally what I just
Yeah,
said.
it's related to the FTR. So
No,
a
I'm
band-
saying like in biology and in proteins, it says there's a shift in these 3 bands. What are these bands?
Okay, we need to check which are these bands. Maybe OH, maybe. It depends. Functional groups in organic. It's the same thing in organic chemistry. So every band corresponds to a functional group, correspond to a carboxyl, correspond to a some part of the molecule.
epoxy or something. Yeah.
So that's the band.
Yeah.
It looks like they're, depending on what is attached to the amide, they are numbered differently. So like
Yeah.
amide one has, I'm just looking from freaking like the internet right now. So like primary amide one has nitrogen attached to a single carbon.
So that's
Amide-
the band of nitrogen with I don't know, the vibration nitrogen hydrogen maybe.
Okay.
Oh,
Right?
No,
so
it's the amount
amide.
of carbons attached to the nitrogen. So if you have your nitrogen on the end, if you go back to like the first slide where you showed the
Yeah. Yeah, these guys.
primary is going to be the NH2.
Ah, okay.
Very end. Secondary is going to be NH in the middle, and then tertiary. There are some side chain groups that have tertiary. meters.
Just N.
So that's what they mean by amide 1, 2, and 3 protein bands.
Yeah.
Yeah.
that's the like the carbon, nitrogen, carbon, whatever.
Yeah,
bands,
most
okay.
most protein have the.
Well, no, it's not.
Yeah, makes sense. Yeah, that's it. That's it.
In my 1, 2, and but for this one they also have in my 3. They are the 3 most common one.
This is 2.
And they know that the MI2 and 3 bands, a shift, like an increase, means that the beta sheets are being created.
Yeah. But I also don't know why their shift means the beta sheets.
I assume it's like if MI2 and MI3 bands are like the secondary and tertiary, so what is this? So like
See.
nitrogen, hydrogen, and then like some other bonding in the large thing that we were looking at. I assume that because beta sheets are bonded together by hydrogen atoms, I'm assuming that they're trying to quantify, like, we want more, knowing that we have more beta sheets means that we would have more hydrogen bonding. And so when they're looking at those amide bands, they're like seeing that there's a shift in the band to an increase, which means there's an increase in hydrogen bonding, which probably means that there's going to be more beta sheets, is my
It's in the
assumption.
opposite. If there is a decrease in hydrogen bonding, we have more beta sheets, right?
I thought beta sheets were quantified by hydrogen bonds.
I think they said they were not related.
They're not related?
Yeah.
They said it's not
They're not
I
related.
literally looked it up.
Yeah, because see, this is I don't know. This is primer amide, right? This is when they are talking about use one radical, use one substitution here. This is carbon, like a chain of carbons. Here's when you have a secondary. This is
Is it
when
a
you have
C, C or
tertiary.
N?
What? This is N, but I mean this R means chains of carbons, right? It depends the molecule that you have there.
How does the number?
So
of
the
affect
the vibrations in each of these functional groups change. That's why the band change. So if you have these with more hydrogens, we have more beta sheets, according to me. If you have these, you have more alpha sheets. Sorry, this one, alpha conformation, whatever. But if you have these, you have more beta. So they are looking for this, which I think is the shift.
Okay.
What are you doing? The thing you are doing is the same. What's the difference?
No, it's okay.
What?
No, it's really different. This is just one carbon chain.
But it says
So this is
beta
primary.
sheets are formed when beta strands self-assemble and are connected by hydrogen bonds.
Yes, that is, yes.
Yeah.
So I was right before. The increase in hydrogen bonds, that they're saying that there's a shift in those bands, meaning that there's an increase in hydrogen bonding, meaning that increase in hydrogen bonding means there's more beta sheets.
See, that's the annoying thing, it's not necessarily. I mean,
Yeah, I
But do
don't
they
think
mean
it's
that beta
necessarily.
sheets are bonded like one sheet, like in the sheet, there's hydrogen bonding, or is it from sheet to sheet there's hydrogen bonding?
Yeah, I think, yeah, if it is from sheet to sheet, maybe. Oh, no, both, right?
I mean,
I
that
don't
would
know.
be tertiary. Tertiary or like their secondary arrangement, alpha helix.
Yeah.
Because it says hydrogen
That'd be-
bonds connect the beta strands laterally, forming a pleated sheet.
Yes.
So there is
Mhm.
hydrogen bonding in beta sheets.
Yeah.
Then why did you
that's
tell me that
Yeah.
there are no hydrogen bonding in beta sheets?
There
are
is,
hydrogen
there
bonds,
is.
And there are
But
also,
I mean, in the alpha, it should be more hydrogen bonding,
How do you
right?
get that?
No?
Why alpha has more alpha?
No? Because
No.
you have this
But that-
conformation, so
that happens every 4 peptides, I think.
yeah.
Whereas for beta sheet, it's every other, I think. I think.
I don't know.
So, internet can totally tell us this.
Because when you have this conformation, the conformation is stable due to the hydrogen bonds. That's why I thought more hydrogen bonds in the alpha. Maybe I'm wrong.
Beta sheets have more.
Have more?
Yes.
Yeah.
Okay.
Yeah,
That's what
because-
I
makes
was
the
wrong.
pleatedness of the sheets is there's more hydrogen bonding.
Okay.
That's why I was thinking or assuming that these amide
So
bonds are
in that
shifting.
case, this changed to the opposite. They are looking for this structure, the first one, not the third, secondary and third.
But they still say it's unrelated to the formation of.
Yeah.
Which is what confused me when I saw that because I was like, I
Yeah.
swear to God, I looked this up when I read this paper and it said that there an increase in or at least like these beta sheets are characterized by the fact that there's more hydrogen bonding. That's what creates the pleat, and the sheets are therefore more structurally like significant.
Okay. I think you are absolutely right. The sentence that says that is confusing because the sentence before it says for 600 degrees, the pressed spirulina, whatever, then those increase in intramolecular hydrogen bonding is unrelated to beta sheets because it's too low for the beta sheets to form.
Mm-hmm.
That's their point. So they're saying that's unrelated. That has to.
Yeah,
do
I don't think they're
with
saying the
other
hydrogen bonding is unrelated to the sheets. I just
in
think
the
they mean
second part.
Yeah, I
I
just think
think
they mean as a function of temperature, those hydrogen bonding isn't what's creating.
So I'm reading here that this sentence, our data collectively suggests that the processing of spirulina powder with heat and pressure leads to changes in covalent bonding and enhances the secondary interactions between the biopolymers within the biomatter.
Yeah, but that's unrelated to beta sheets.
Oh, is it?
That's saying.
So what are the two things covalently bonding?
It's saying aromatic compounds in blah blah blah. So you have different groups,
Okay.
side chain groups. Some of them are aromatic, and they have dangly bits with O's and whatever. Those react, and those make more CC bonds.
Okay.
So that's more intramolecular complicated things. But I think what it's saying is ignore the sentence on the unrelated to formation of beta sheets because that's only for 600 degrees. For when it's actually talking about increasing the strength, the increase in hydrogen bonding is related because
Yeah.
you were 100% right. I just
Yeah.
think that sentence confused.
Yeah, wait, what sentence is it? Because I actually wasn't even looking at that sentence.
Page 5, first paragraph.
Oh, I see.
Mhm.
Yeah, may indicate an increase in intermolecular. Oh, yeah, may indicate an increase in intermolecular hydrogen bonding that is unrelated to the formation of beta sheets.
So yeah, that's the. So it also says the more significant redshift in the OH bond in the absorption expression for the same sample at 140 indicates more intermolecular hydrogen bonding.
Yeah.
And that's how you know that they transition from beta sheets, alpha to beta.
Yeah.
Alpha to beta.
So I think that's why we were getting confused.
Yeah,
So we were looking at the first part of the.
Now makes more sense.
Oh, I see. Okay.
So
So then that particular temperature
We're
is
all
unrelated
right.
to beta sheets. Okay.
yeah, well, for anything above 120,
It's related to beta.
it's related to beta sheets.
But since this was at 60, it's
Yeah.
not related.
'Cause
Okay.
it- yeah,
Yeah.
because it didn't form. Yeah. So it says for things below the formation, they increase strength. So everything below 120, the increase in hydrogen bonding is related to different biopolymers present, and you have increased intramolecular bonding,
Yeah.
H bonding, whatever. But when you're above 120, you have an increase in intramolecular bonding. I'm assuming it's greater than the bonding they see at the 60,
Mm-hmm.
and then that's related to the transition from alpha to beta sheets.
Yeah.
Because I
Beta
assume
has
there's a
more.
certain temperature that's necessary to be able to break enough bonds to then create more hydrogen bonding for beta sheets. And I assume
Right.
that happens at around 120, 131,
Yeah.
where we have whatever
Right.
temperature.
That makes
Yes.
a lot of sense.
So, yeah, here's a component. You can see there is not only.
Wait, can you share it? Okay.
How can I share it?
Aren't you presenting?
No, it's not.
How is it?
What's happening is.
because you're on the. I'm
Yeah,
right.
yeah.
I was like, I was really confused for a second. Okay.
Just yeah, it's okay. Just the thing is for alpha helix, it has not only hydrogen bond but also something else like the CO bond. But for beta sheet, it only has hydrogen bond.
Oh, okay.
So-
That's what I was confused.
Yeah,
I
and,
was thinking is more
still,
hydrogen bonds in the alpha.
Yeah, still so for beta sheet, it only has hydrogen bond.
Mm-hmm.
Mm,
Cool.
okay, cool.
Okay.
Let's go on.
Okay, so yeah, that said, then they suddenly realize they need to sonicate their cells, so they sonicate the cells, and they find out when the cells are, the sonication is better because yeah, maybe they made them have more proteins. So they do the SEM to verify their assumption, and then they because they already proved their materials had better mechanical properties. So now it's time for them to find some to add something in their materials to make their materials better. So first thing they did is So let's look at the figure F. Super small. So for figure F, there are 4 different lines: red, blue, yellow, and purple. And the yellow lines is their pure material. They did not add anything. And then the blue lines is after the. Let me check. It's after it's sonicated. So we can see the blue lines is because the modules of the blue lines is a little better than yellow ones. So and it's almost the same as the red one. So but still both of them are better than they're the pure material. So they think that the red ones is really great. So the red ones is what they add. Okay, so red ones is what they add. They add the nano clay, so it's MMT. I don't know why they choose MMT, because usually during the bio paper, if they need to add nano clay, they always choose MMT.
I think these are paper people doing bio stuff.
What?
People, NC, the paper people like to use NC as composites.
What's the group?
With, I don't know. I don't think it's a paper person in materials.
It's University of Washington.
University of Washington. I know the professor.
University of Washington has paper people. Yeah. It's like one of the few places with paper.
They work in the same building I used to.
Yeah.
Yeah. She's
So I
more of
think
like
that's
a
why they chose
polymers person, but I don't know.
I also don't understand why they layered the bacterial cellulose instead of mixing it in. So I'm mad about that. They should have made this material way better.
What?
So the bacterial cellulose, they did like sandwiching, which is why their data is so wackadoodle. Because if you look because they're just seeing the flux and toughness from the bacterial cellulose, not actually from the polymer, because it delaminates at the interface, not one or the other. If they just mixed in the bacterial cellulose into their material.
Yeah, that's what I was thinking. They're just doing the sandwich, like the layers are the bacteria thing, and in the middle is their original material.
Yeah, I think it's to form strong multi-layered structures characterized by a vast network of hydrogen bonding. So I think they wanted to maintain as much hydrogen bonding connections in those layers as possible. From mixing?
From mixing. Mm-hmm.
Huh.
The more broken down the cellulose is, so bacterial cellulose, it's basically you take paper, pulp, and then you break it down so much that it's just like these nano strands, which are, and if you've seen cellulose, it's just like a sugar, and that has tons of oxygens that can do hydrogen bonding. So the more broken down it gets, the better bonding it does. So for adhesives, people are mixing in nanocellulose or bacterial cellulose to make it stronger, especially like wood adhesives or whatever. That's a big thing right now.
Yeah.
So I don't know why they do that.
Maybe it's for them to achieve this in plane tensile strength, like they're trying to achieve a certain like direction of tensile strength.
But
So maybe
that's just the bacterial cellulose.
yeah.
Because it's strong stuff. Like
So maybe they don't wanna
I don't know.
cut the cellulose to very small pieces. And they make them into a sheet.
Yeah, it just says aiming to capitalize on the high strength and stiffness of the self-bonded sheet. So I guess that's like as grown.
They could make a lot more money if they looked that up. Just saying.
Yeah, that's maybe that's the reason why the result is that's not good. Yeah, that's what the purple one is even lame than their original stuff. The yellow line. So
Also, it's the most error.
But the red one is the best one, right?
but the toughness is
With
In
nanoclay.
terms of like, there's like
Flex
stress,
stress,
yeah, but the toughness is much better. So I don't know.
toughness is low.
They should. I don't know if they mix them all.
Yeah, nanoclay, like
They're not going to ask
it's
about
a
that on the
ceramic.
exam, I can tell you that.
I don't think so.
And then purple one is just good, but
Cellulose types. Toughness. Wait, like the
Use a napkin.
bacterial cellulose, is it like what's like the structure? Is it Okay, they are talking about stripes, so it's in the form of like threads or something.
It's regular cellulose, it's just produced by bacteria
Okay.
instead of being cut down from trees.
Yeah, it's
That's not my job.
it's like nanofibers woven into a
Fibers,
3D
good.
network.
Yeah, because I'm just thinking about like why the toughness for that is higher than the clay, and I'm thinking the clay would be like powder form or something. So like in terms of how it goes into the matrix, you're forming a composite, like something that's more like, as you're saying, thread like fibers is gonna improve like toughness as compared to like powders.
Yeah, and I think the nature of the bacterial cellulose is like, because it says, like when I looked it up, like overview wise, it said it was woven into a 3D network, and I think the strength of it itself, really good mechanical properties, and also water holding capacity.
Yeah,
So.
it's just gonna
Into a
help with,
3D
like,
network.
effective bonding.
Into a 3D network. I didn't read the paper, but into a 3D network.
Yeah, that's all cellulose. It'll all do that. Even if it's broken up, it'll still form into a 3D network.
Yeah, and then the nanoclay, it just says like high aspect ratio and also better mechanical properties.
But how you
I think it's
understand
just like
in the
powder
in the figure A, right? We have the unprocessed one and then sonicated one, right? The SEM image. And if you notice, the idea with sonication, according to my understanding, is just to create, to separate if there is some kind of layers or flower-like structure, whatever. They are using sonication, right, to spread all of that, right? So
to make them more
Surface
uniform.
treatment.
Uniform.
yeah, so you have a actual that I don't understand that's not 3D actually. That's more similar to 2D because we're spreading.
Oh, the 3D is not. That's not the broken up. It's the cellulose. Look
Yeah,
at
it's
the-
for like
when you
the
add
additives.
when you add the additives. But if you look like with the bacteria, you say, right? Okay. Yeah, because with the nanoclay, it's like again the same image is like 2D.
So
Yeah, but this chart I think is no additives.
Oh.
No, but the image, the E is with the bacteria, right?
Yeah, well,
Maybe with the D,
actually,
the last E
like
is
the
Yeah, with
structure.
sonication.
Maybe, this one.
But I don't think you can compare the chart in A to the thing in E, because the chart in A is just spirulina sonicated,
Yeah,
not sonicated.
without-
Yeah, for
no
sure. Yeah,
fillers.
we can.
Yeah.
You're right. Yeah.
So why do they use the cellulose made from some bacteria?
because they want to talk about being pregnant.
Yeah,
It's not
yeah,
as efficient
yeah.
as making cellulose, using cellulose from trees or other plants.
Yeah.
There's also like cellulose made from like eucalyptus and straw and all this different. It's like a whole thing.
Yeah.
But the most environmentally friendly one, because you don't have to cut anything down, is the bacterial cellulose. However, the yield is not as strong, but people like talking about it.
Oh, so it's more about their big ball protect the environment.
But it's not commercially viable. Whereas there are other forms of cellulose in it.
I know. I heard it's not easy to use bacteria to grow something.
No.
Okay.
Can I have one of these? And look, Emily
I
eating a
also-
lot and.
Well, you made them. I also want to comment on the image in C.
In C.
All of their profilometry images are terrible, I
Mhm.
believe, because the contrast is terrible. How
Yeah.
can
I really wanted to
Yeah.
understand. Actually, that's my question. Can you explain this because I don't have any
Oh,
idea
yeah.
this
Oh,
problem.
yeah. So, everyone knows AFM?
Yeah.
So, imagine AFM, but instead of on a nanoscale, you're on a micron scale.
Micron. Okay.
So,
Big needle.
yeah, exactly.
What? Say it again.
It's a big needle on a stick.
Oh, okay.
So,
Opposed to a really tiny needle.
yeah. For these images, you want really high contrast. If you go back,
But they have that SEM, so like why?
well, you don't get roughness for SEM. Yeah, so you can see the yellow, the first image with the yellow and the blue, I'm like, that's great. You have high contrast, I
Yeah.
feel confident that their SQ, that's the average roughness.
Yeah.
Yeah, well, yeah, you just
Okay.
can't. But the bottom image, which I don't like, because first off, they changed the scale, but the scale's
I
not
was
changed
just
enough.
about to say the change scale is like what irks
Why they
me.
change the scale?
Yeah.
Especially
It's
because I
200
just made a
micrometers.
poster where my advisor was like, you need
Wait.
to change these. And I was like, oh yeah, that makes sense. And now I look at things that aren't like that, and now I'm like, well, come on now.
What do you mean change the scale? It's
Wait,
200
I don't
micrometers.
think
0 to 38 in the
involves-
height
No,
scale
I'm saying, I don't
for
think
the,
it
this
involves,
bottom
like, a
image,
tip or anything
Yeah.
like
and then
that.
it's 0 to
0 to
12.
12,
They need to
yeah.
be at the
Yeah.
same length.
Yeah.
They need to be at the same.
0 to
I've done
where?
optical
Show me.
profilometry in chaos.
Oh,
They need
yeah,
to be the
yeah,
same.
yeah, for sure,
Yeah.
for sure.
That-
To compare, like, yeah.
So
Yeah.
they're not using
Yeah, that's-
optical profilometry, I don't think. I think they're using normal profilometry with the. Either way, optical profilometry also can't get resolutions of 0.4. They can. I've done that, but they can't get much lower. And because they're not seeing a lot of difference between the extremes in this image, I do not feel confident that that's actual roughness.
So you're saying this is profilometry, not optical profilometry?
Yeah, I think so.
No, this is optical profilometry.
It says that?
Yeah. It says, like right here, figure 4C, optical profilometry.
Figure 4C. Optical profilometry. What did they use?
I think they used the cans. I was so happy. No, maybe they didn't. That was
Okay, they changed the height,
But
but
they should have used
but
the
it's 200
profilometry.
micrometers
It
more.
would
Oh, here
have
we-
been better. The
yeah.
problem is with the cans, you
Yeah.
need something to
I think it's just
confirm
wrong.
that, because it's not
So-
as good if it was low.
Because
Yeah.
both images
Scales.
are 200 micrometers.
My advisor literally
like when
was
you're
like,
doing
I do
ATM.
not trust the key.
If you have the same 100 like nanometers and 100 nanometers, it's the same thing.
No, that's skill. That's
Yeah, yeah, I understand the height.
Like
What?
you wouldn't be able to quantify because like see the difference.
Yes.
Like
Oh,
zero
yeah.
is like very
It would break it.
like what
Especially
purple and
in that top
red
one,
is 38.
It's
But
mainly
here,
yellow,
right?
which is what in the
Yes.
20s, which is like.
Do you understand? Like
Yeah, yeah, I
here,
understand.
something that's yellow here is like 8. If it was in the other image, it would be purple.
Yeah.
Do you understand?
Yeah.
So it's not giving like
But
a
they should have changed the scale more,
yeah.
which is why I don't believe in these images. Optical profilometry. Oh.
That's a good thing to critique, maybe.
At 20x objective, contact profilometry was conducted using a Buchner DECTAC. Okay. So that's the same one we have to clear.
Was that what they used for the?
I do not trust their results.
Never use
They use
profilometry.
20x objective. That's it?
Not if Rebecca is looking at your work.
That's what I do. This paper minus the bio is what I do mostly. But well, it's one of the things. Anyway, so I don't trust those references.
Yeah, I don't think they are doing it so good. But
No, it's okay.
yeah, but it's still a process. Okay, so yeah, so based on their paper, they said their current staff never use any addiction, and then they add the working. So in the paper, I believe they spent a lot of graph talking about why others use this one. They try to use this one.
Yeah, I know.
Yeah, and it looks like this one is better, but the thing is, they're still do not go with their goal of very clean stuff. But it's okay. So they, I don't know why they do it. Just I don't know why they thought to do sales liquor. So, but still okay. So they use their cell powder and mix it with plasticide, and then after the hot press, they still get it back, and then they said the extensibility is increased, and did they see in the paper how much is increased or just increased?
I have a question about D.
Yeah.
Because I would expect it to increase like linearly, right? Like it has 0, 1, 5%, and then 30% is
20%.
below all of them. I don't understand why, but I don't know
Yeah.
flexible stress versus strain that well. Anyone have an idea?
Structural stress versus strain.
I think it's the same pattern as
But it's not the same because it's below, right? Exactly. It's
30% is
Structural is just like a 3-point bending. I don't
I
know.
think so.
Yeah, that's what it is, and that's how it is compared against like
Right.
say
But the
pencil or
thing-
something.
Yeah, in the paper they just bend it, or they said how much it can bend.
That's why I didn't choose bio.
So how do they see the
Science.
We said a 3-point bend, right? So you have a piece, and then you have a bar, and it goes, and
Yeah.
then you
Yeah.
measure this.
okay.
So that's what they're measuring, and then it breaks at a certain point. So if it breaks here, it'll stop. So at 0.5 strain,
Mm.
right? So at 0.5 strain, it breaks. But then it's saying, I guess, the bottom one can do this.
The Young's modulus is the
Yes.
slope of the initial line.
What? Say it again? The Young
Yes.
The
modulus?
Young's
Restriction.
modulus
Mhm.
is the slope of the initial line.
Yeah. That's
The initial line before like
It breaks. The
before it does
before
like
it does
the little
yield
scoopy
strength.
thing. Yeah, that guy.
But the 30 has a lower slope, correct?
Yeah.
So wouldn't that have a lower Young's modulus?
It
Yeah,
would.
less bending?
But it doesn't mean that it's any less tougher. It's more tough because even though it's bending, like its onset of strain. Oh, it also doesn't mean that its yield strength is any lower either.
The first three materials are like what's it called? The linear part of like the stress strain curve is the elastic part, and so it's the material until it like breaks, and then the like rest of it is all like its ability. What's it called? Like the I forgot the word, where it like bends and it won't go back to its original form. So this is basically saying that this, so this, the 30% one is basically saying like you can bend this material like crazy. It may not be like super strong, but like its flexibility is really, really good. And these points where it ends is where it basically breaks. So these materials are very brittle in that they don't, they're not able to bend very well. They, like as soon as you put any stress on it, it immediately cracks. But this other one, which is shown to be like you can bend it a lot, which like maybe it's not as strong necessarily, but its flexibility is really, really good. And so that's where it starts to break at this like almost 2.5 strain.
And I think they are trying to make the case like depending on your application, you choose what ratio you wanna do it. If you want something which is an application which is flexible, you can use 30%.
Because a lot of materials you don't want them to bend, you want them to break upon like immediate. It's usually like, what is it, 10% of the surface area crack or something like that. Like you want an immediate break versus some materials you want to be able to, well, plastic deformation, that's what I'm thinking of, is when it's like you reach elastic form where like you can go back to its original shape, then you get into the plastic range, and then
you can go back.
I think maybe we should
But I agree, the like different applications is like what they were trying to talk about.
Plasticizers make a difference in the material. Like in this case, what does it do?
Thing to know.
Like, is it like a cross-linking thing or what? Like, because we need to know like the mechanics of how this orbital.
Wait, so like I haven't read the paper up to this point, but is it that like after they did everything with the nanoclay and the other stuff, then they decided to add something else to see what happens?
They said they add the sorbitol to as alternative.
Alternative.
So I don't know what that means. Suddenly it just changed to that.
To plastic.
Because I think all the other ones kind of had like weren't too good in toughness. Like you see all these things kind of had a very immediate failure.
Yeah.
Except for this one, which had the little fibers and shit, right?
Yeah.
So then, if you want to like bypass the fibers but still have good toughness, then that's why they add the sorbitol.
Wait, isn't that what we wanted though?
I think.
Yeah,
No, we
it's
wanted
like
more.
it makes it soft and bendy
Yeah,
and like increases viscosity.
and that's a different like if you want to.
I
make,
just
like,
don't know how it's
gaskets or
bonded.
something.
Like I don't know how the plasticizer specifically like
Oh, okay.
molecularly interacts.
I think I
with
get your point. You are trying
Yeah.
to say that like
because
this one
is-
we're able to get like high flexural stress and also get the toughness.
Well, it
With the
the
same-
plasticizer decreases. Oh no, the higher it does have a higher
Yeah, it's high
flexural stress. It
flexural
has a lower
stress. It
modulus,
also
but
has like
yeah,
good
but yeah,
flexural toughness.
yeah,
But
like what mechanics with the cross-linking or whatever the
Mm-hmm.
plasticizer is doing, like how are those like directly affecting the mechanical properties? I think knowing that and maybe knowing a little bit of like fracture mechanics would kind of help because I know
Yeah.
I went over that in undergrad,
yeah, as you're saying like
like crack
So,
propagation.
yeah, like,
and
yeah.
adhesion between like matrix and like fillers and stuff like that.
yeah, like toughness is basically like how much energy the material can absorb before like it finally just gives in, right? And that's why I was asking the first question about like what's the structure of like the bacterial cellulose, right? If it's more like fiber like, more thread like, it's gonna form networks and then it's going to be more difficult, like it can absorb more, right? So for this one, like it's a plasticizer,
Yeah,
right? And so because of that, I feel, I haven't read the paper, what I feel is that it's just going to form a more strong bonding with your material, like the matrix material, and so it's going to be more difficult for it to then like break upon applied stress. Like it's going to absorb more stress basically.
I understand that, but sometimes maybe when you're doing this sort of plasticizer, it creates more of a bond within the matrix, and at that point it might exclude whatever the fibers and stuff, like that sort of material.
I have a Wikipedia page that may help.
Okay.
So it says plasticizers work. Well, it was commonly thought that plasticizers work by embedding themselves between the chains of polymers, spacing them apart, and increasing the free volume of the polymer.
That'll be bad.
Well, I would say it's good.
It's good.
Yeah, so it decreases friction.
Okay.
It makes them more bendy.
Mm.
Yeah, because it's more free volume for the chains to move, which is
Okay.
what causes the plastic.
Good.
Just like if you heat up a piece of plastic, it becomes bendy. It significantly lowers the glass transition temperature,
Yeah.
making it softer. Then it was also shown later, and lots of complicated things, sometimes plasticizers reduce the free volume. So there's questions about if that is a true thing. But
Yeah.
the internet says that it just depends on temperature and the concentration, and that's pretty much it. No one really knows how it works.
Yeah.
But if they're going to ask us, we can say the free volume thing, and I think that would be totally fine.
Yeah. Because I feel like the argument for like decreasing free volume could also be made.
Well, yeah, it says in the
It could decrease
hydrophobic
and increase,
sections,
yeah.
it would, depending on the plasticizer, it
Yeah.
could decrease the free volume. So
Did
then
they
those
say anything
rates
about
would stay.
temperature they did this?
The
If
only
they
thing about
didn't,
temperature
like,
is,
then we just,
compressing.
That's a good question. They should have done something with temperature. Why? Yeah.
Yeah.
Like I wonder if this is all with like 140. I'm assuming.
Yeah.
What if they did this from 120 to 200? It might change the temperature range of the bacteria.
Wait, you're talking about the plasticizer or actually
Yeah.
within the testing conditions?
No, like for the new plastic, so making a new plastic with
What's the
the plasticizer, so it might completely change the properties of the plastic.
Yeah, maybe. I think they first get to the conclusion that
It's
in
better.
the beginning 140 is better, and then they never change.
Yeah, so they just focus on that.
Just
Yeah.
go through.
Because like it might not be better for the other things they're adding.
Yeah.
I
Yeah.
wonder if they tried that.
It also mentioned the sorbitol being the first part you mentioned about plasticizers, where like it's introduced into the formulation and it melts and forms a cohesive matrix around the cells. The intact spirulina cells can efficiently bond together through the sorbitol matrix.
Yeah.
So I think
Okay.
I
The
think they
bond
must
is a
have
big
saw
thing.
that and was like, oh, plasticizer in this case is good, and then moved on and
Yeah.
didn't do any temperature
Right.
stuff.
Yeah.
But I think that from what I remember, the way these what I'm saying is that why not have the fibers on top of the plasticizer to create something that's more like rigid, right? A stronger elastic modulus, and actually, wait, did the fibers decrease elastic modulus? Actually, scratch that.
I
they
think at the
decreased
end of the
elastic
day,
modulus.
you have.
Yeah.
Wait, are you saying we have the cells, then we have the fibers, and we have the plasticizers? So that's like a hybrid.
Actually, I'm looking at the nanoclay. Like, why not pair up the plasticizer with the nanoclay?
So to form a hybrid,
yeah.
maybe they didn't want to do that. But that's something also be
I
interesting.
mean, that's what plastic people do. They
Yeah,
shove
they
a
put
bunch of
carbon
crap
black and
together.
stuff.
Yeah. Maybe they didn't want to do that. And
But-
like, that's what I was saying. Like with this material, they have high flexural strength, but they also have
Your mom?
good flexural toughness, right? Because with hybrids, when you add another material, it also cost, right?
Yeah.
And maybe compensation of the how do I say
Performance versus
the disadvantages of one over the other and compatibility issues as well. So
Okay, go ahead. What's missing?
Hmm?
Go ahead. Like what's missing? That's all.
yeah, I think
right?
Clary goes on.
Okay. And then,
Do you remember that the failure mechanics happened at the interface with the fibers? They happened at the interface between the fiber and like the matrix.
That's
So-
for the bacteriocellulose.
That's bacterial cellulose.
Yeah, which makes sense. The other, that's not what the other ones are.
Yeah, yeah.
For the nanocellulose, it broke within the material, it was integrated.
Yeah, because the fibers will be more interwoven in there.
Oh, so nanocellulose.
Well, they should, they didn't break it up, which is of course why it broke. Yeah.
They had one of nanocellulose?
That's what the bacteriocellulose is.
Bacterial cellulose.
Oh, okay.
Same thing.
suppose this one, they just add those sorbitol to the regular one. Yeah. They do
Yeah.
0%. Is sorbitol something regular in our food?
I don't know.
I just think if you buy
Let me
every
look it up.
You are here, the
What?
expert.
It's a sweetener?
Yeah, I didn't mention it was a sweetener in the paper.
They did mention.
Actually, maybe I looked it up and I saw it.
Sorbitol is a sugar alcohol.
Ah, yeah, look at that.
It's a drug.
It sounds like a drug. I know.
A low calorie
It
sweetener.
sounded familiar. I don't know why though.
Sorbitol.
Don't have Splenda or any artificial sugar.
Oh,
Yes.
okay. And then they
Long reasons.
Okay.
Okay, and then they compare their what they get with other material. The other material like the PLA, PHA, TPS. They mentioned in the beginning of the paper like how they are not as good as, for example, they have a lower strength, more draws and something. They try to compare, but based on their two figures, the two figures in A, it's like. I don't think their material is like way better. I just think okay. So
I look at that chart and I think cellulose is way better than all that other crap.
I know. So it's like,
But it burns. So.
oh yeah. So that's why
Okay,
they do
okay.
the.
But it burns too.
Yeah. But it looks like their material can be self-extinguished in a second. So. They said so that's why they are better. Right. Because the others just burn to pieces.
Yeah, I think the main thing is like TPS and PLA are very common, which is why I think they did the extrusion part, like why they created spirulina, because PLA and TPS, they're big plastics that are used in 3D printing, which is a very common, also in injection molding as well, which is like how most plastics, I think, in like literally everyday use are made.
Yeah.
And I think they want to compare it to those plastics because those plastics specifically is what's made more commonly in industry. And those plastics are, in theory, PLA is supposed to be like better for the environment than other plastics, but it's really not, which was like a big thing in the 3D printing industry when people were like, oh, it's better, and then in reality it's like it's really like there was no significant, like there was some change but not enough to like actually create any significant like environmental impact.
I feel like it's made out of corn, right?
I think so. Yeah.
Then you gotta make corn.
Yeah, well, I think here they mentioned like corn, wheat, and all that stuff, and how like that's just like not good. So
Well,
it's just like
why not?
Sure.
We have so much corn. We can make corn so much faster than this thing.
yeast and
they
wheat
said
and shit.
the
That's true.
production of about corn is very it's a little strict. It needs some money, some
Needs
work,
money?
and so
There's
yeah,
so
and it
many
takes
people
like
who don't
water
grow.
and
I think like algae can grow anywhere too, so.
yeah, they want to grow it just beside their
Okay.
experiment building. So
also being able to like take current plastic manufacturing infrastructure and not having to build new buildings and stuff like that, I thought was a very interesting part of this. They were like that, I guess that was like something that they definitely considered was like we want to be able to use existing infrastructure, which makes sense. Like it doesn't make sense to create a whole new system when you need new buildings and new machinery and like new like cut down forests for new places and stuff like that.
Yeah.
So.
Okay, so they show their material is way better, so which I do not believe. It looks not like this, but it's still okay. Yeah.
It's good.
And
They're dying.
Yeah, and then finally they come to their most important part. Their material is super clean. So how do they verify that? They put their material into dust and then through that circulation we can see they first take the generation 0 and then they
Biodegradation is really good.
after grinding them to powder and then they come I think they wait. What was they do? Oh yeah, they put them in the dirt and then after some time they measure their strength again, try to figure out is it become way worse. But the thing is, they only show the sixth circle. That means they have the generation 5th, and they said it's enough because they already know that after 5th it's already the strength is going down. But through that figure, I think 5th is better than 4. So I don't know why they just thought you could like make something kept going down, and then they said, oh, it's screwed.
They like the maximum though.
I didn't like this either because I was like, look at the amount of error that's on that graph.
Yeah.
Like, I have zero confidence that this thing is gonna be any because they only did what 5 trials and that much error.
So I think it should be like kept going down, then it's okay. But 5/5 is better than 4.
It is weird. The trend doesn't make any. Well, the lack of trend doesn't make any sense because like that's the big thing also with PLA is like as soon as you go to melt it down and remake it, it's like mechanical properties decrease like considerably to a point where like it's not even like a useful plastic anymore to be used for like anything other than like hobbyist work.
Right.
And in theory, like it should go down considerably, and like it might hit a plateau at some point. I don't know like when in the generation cycle, but it should, especially 1 to 5, should be decreasing, not like go up and down. Like I really don't understand
wish
it,
they-
which maybe talks to its ability to be able to be regenerated, but
I would
just
say
don't know how to
I don't think
reproduce
so.
everything.
it talks to the ability and the variability between trials.
yeah.
Because like I wish what they did is they color coded each run so that I knew which one from 0, 1, 2 was going on. Because maybe the top bars for all of them was the same batch that they were regeneration.
Yeah.
You know?
Yeah, maybe they mix it all
So
up.
it could be that the variation between 35 and 25 creates that much craziness. I agree. Because
Display of that.
if it because let's say the one from 35 goes down to 15 then goes back up to 35, like that says nothing to me. You know?
Yeah. Oh, you mean they should try to make.
Like keep the samples the same and grind them up and make new samples out of the old exact same sample.
So they
Oh.
know
Yeah.
the exact strength from each batch. Like
Yeah.
instead of combining, they have that data. They just didn't express it like that.
Yeah.
Because it
Showed
probably,
wanted.
yeah, 'cause it probably showed a huge variability.
I'm thinking they probably just took all the samples and ground them up,
Or they lost track, yeah.
right?
Yeah.
Well,
Or it sat too long.
Like all at once, kind of just grinding them up.
but they ground up everything 5 times. They ground up 5 different samples 5 times.
Yeah, but
That's what that tells me.
I'm saying that they took all the 5 samples, ground them up in the same grinder at the same time, and probably made new.
They
5
wouldn't be able
samples.
to do that because
They have
then
5
you
distinct
would have
data
1
points.
point instead of
Yeah.
5 for the next one.
But then they could just make 5 new samples out of the old.
Why would you do that? That would be like a lot more work.
What do you think they're doing?
If I was doing this experiment, I'd want to do this 5 times. So I would take the same W that they like to have in this paper. Now I just do that 5 times.
So each of those points isn't a single sample.
It is a single sample.
But like we don't know if like the first point in the first generation is
Oh.
the same as the first point in the
Yeah,
second
yeah.
generation. Like you don't see that because that would be a lot more helpful.
Yeah, there's some marks
Which
on
maybe that's why they did do that because they realized that it would have been bad data
there. Yeah.
or like like
yeah,
data
smart.
that doesn't support their.
Yeah, so then the only thing they show is during the figure D, they said their material is as good as banana peel because they have the. Okay.
I like that.
That's weird because their material was dehydrated, but the banana peel wasn't.
Their material was dehydrated. What do you mean dehydrated?
Like the spirulina
some
powder has no
water?
water in it, right? But then they're like putting it against a banana peel, which they didn't dehydrate.
Well, it doesn't
So
matter.
degradation. I mean, you're losing a ton of a lot of the mass on a banana peel would be water.
Once you're in weeks. So you're gonna absorb, if you're a bioplastic, I don't know the they don't have contact angles or anything on
This
here.
isn't scattered too. It's pretty much.
Right, so we don't know
I don't want to
how
follow
much
an
water is
experiment
in
for
this plastic.
25 weeks.
We just know that
That's the only thing that I don't
starting
like about
material
bio.
is
I don't want to
dehydrated.
follow
We
an
don't know
experiment
how
for
much water gets
25
into that
weeks
material later.
every day and go and take a
I'm
picture.
assuming
Day
that
1,
it
day
has
2,
similar
day
amounts
3.
of water once you're on week 2.
Oh,
They're
because
probably
things
going
get
every 5
rehydrated as the
days.
experiment goes on.
Yeah, I don't think they do that every
Or
day.
they're making
Yeah.
some like undergrad do it, or
Yeah.
like some like first year grads. But I don't think they're,
Yeah.
especially because if they're going from 0 to 25 weeks, I don't think they're
Weeks.
looking at
They'll
everything.
not do every
one
day.
day one.
You
They're
don't
probably
know.
looking at 1 week,
1
2
week,
week,
1
3
week.
week, 2 weeks.
You don't know.
Well, I mean, common sense makes me think that they're not going back every day and looking
Yeah, for
at
sure
it.
not.
Maybe they might, I don't know. How did they know it was 111? It was gonna degrade.
Oh,
I
that's a good point.
You know?
Excellent.
Well, probably
Good.
because they had data that like
No.
happened
No,
throughout,
just
and they
once.
found.
That took so much time. Like,
No, I'm saying like
Yeah.
they went back every 5 days and looked, or
Oh,
every
yeah.
They
3
didn't
days
notice
instead of every
change and
day.
then-
And then they
So on
probably, when they
vacation,
finally looked at all their data, and they probably
That's-
were at like day 115, and they were like, oh, we saw, or day.
I think they just put a
200
camera to
on
do it
the-
by itself.
Yeah, I
Probably,
think
yeah.
they just decided to take like day one and show like what the difference is. Doesn't necessarily mean that
It
when
was
it's
good.
it degraded like.
Oh yeah.
They probably had a camera set up that
Yeah.
was there, like that, looking at the same location,
And-
like for weeks, and they just had it
Take
hooked up to a
pictures,
battery.
like-
and-
Every day with
Yeah.
the same thing. Yeah.
It's not outside. It's in a box of soil in a lab. It's like it's not outside. I would bet you.
They got a lot of
I
authors.
told-
Maybe one of these last co-authors was the person.
Yeah. Yeah. Let me see how many. Who was the huevón? here.
This is the main professor.
No, this is the main professor. This is not the huevón.
Yeah.
The huevón is bichilin
Put water in a bucket with dirt.
I'll explain to you what a
And put light on
huevón is.
it.
What?
Yes.
Huevón? I'll tell you what that is.
What if a bird takes
It's
it?
too
You're on
dirty.
day
Too
50. You know?
Where's a bird gonna take these plastics?
Make it in the nest. It's big.
Okay,
Naked birds are good.
So
It's true, seagull and toads.
okay.
Yeah.
So
It's shiny too.
yeah, this paper is really for I don't think not much except something about for the fraction we learned. I don't know.
Characterization.
Yeah.
Basics.
Yeah, some technical questions. I'm trying to think, but all I can think is maybe they will ask you why the some simple, very simple questions like ask you to read the figure and tell which is better for which part, which has strength one the best modulus, and for harder one maybe they'll ask them why they use this kind of thing, that kind of thing. But I don't think they'll ask why they use sorbitol or something. But maybe they'll ask like why they use sorbitol, not glycerol, because it's in a fever like sorbitol has a better temperature or something. And if you want to really ask some hard biology questions, just talk about the environment and you can read.
I will answer those papers no matter what questions they ask.
Yeah.
I think the type of peak shifting might be an important book because we saw some peak shifting. So they're like, what if it shifted the other way or something?
I think they're just saying it shifted.
I think that's what matters. The fact that it shifted means there is a difference.
Yeah.
I like this paper. I feel like this is the kind of paper I would write. Be like, I don't know, it shifted. That's all I
I
know.
mean, as a person who's taken one biology class in high school,
You write
I
good.
can-
You do
I
this.
can understand that.
Same. That's how I felt. Though I was like, I know so little about biology. I was like, I don't really want to read this paper. I was like,
Yeah.
no, I'll try and read it. And I was like, oh, it's actually like not that bad.
Fun paper. Okay. We've got how many?
Oh.